Let's begin with one of the most revolutionary moments in the history of science, Galileo's experiments on motion. Back in the early 1600s, people followed Aristotle's belief that heavier objects fall faster than lighter ones. But Galileo decided to test this for himself. Imagine standing on top of the Leaning Tower of Pisa with two spheres, one heavy and one light. You drop them together. What happens? Surprisingly, both hit the ground at the same time, but only in a vacuum where there's no air resistance. Galileo's careful work with inclined planes and free fall showed that the acceleration of falling objects does not depend on their mass or shape. His conclusion? This uniform acceleration is caused by the Earth's gravitational pull, and it acts equally on all free-falling bodies. This idea set the stage for our modern concept of acceleration due to gravity, a force that influences every object, from a falling apple to orbiting satellites. Now that we understand Galileo's insight, let's define the term acceleration due to gravity. It is the rate at which the velocity of a freely falling body increases due to Earth's gravitational attraction. We use the symbol g to represent this acceleration, and it always acts vertically downward toward the center of the Earth. In the C system, its unit is meters per second squared. That means, in ideal conditions, if you drop an object from rest, after 1 second it will be moving at 9.8 meters per second, after 2 seconds at about 19.6 meters per second, and so on, as long as no other forces, like air resistance, are acting on it. Think of it as a constant pull that nature applies equally to everything. Let's connect this to Newton's laws. According to Newton's second law of motion, force equals mass multiplied by acceleration. In this case, the acceleration is g. So we can write force equals mass times g. From Newton's law of gravitation, the gravitational force between the Earth and an object is given by capital G, the universal gravitational constant, multiplied by the mass of the Earth multiplied by the mass of the object, and divided by the square of the radius of the Earth. If we set these two expressions for force equal to each other, the object's mass cancels out, leaving g equals capital G times the mass of the Earth divided by the radius squared. This formula is extremely important because it shows that the value of g depends only on three things: the universal gravitational constant, the mass of the Earth, and the radius of the Earth. Now, let's calculate it. The mass of the Earth is approximately 5.96 times 10 to the power of 24 kilograms. The radius of the Earth is about 6.37 times 10 to the power of 6 meters. Substituting these values into our equation for g gives us a numerical value of approximately 9.8 meters per second squared. This means that if you drop a 1 kilogram mass near the surface of the Earth in a vacuum, its velocity will increase by 9.8 meters per second every single second. This standard value is used in most physics calculations involving free fall near the Earth's surface. But is g always 9.8? Not quite. Its value changes slightly depending on where you are. At the equator, g is slightly smaller. Why? Two reasons. Earth's bulging shape at the equator increases the distance from the center, and Earth's rotation creates a centrifugal effect that slightly counteracts gravity. At the poles, g is slightly larger because you're closer to the center of the Earth and there's virtually no centrifugal effect. G also changes with height. As you go higher above sea level, you're farther from Earth's center, so g decreases. The same happens if you go underground, because part of Earth's mass is now above you, reducing the net gravitational pull. And if you go to another celestial body, such as the Moon, g is much smaller, about 1/6 of Earth's value. So far, We've talked about free fall in a vacuum, but in the real world, a resistance plays a big role. A resistance is a force that opposes motion. For objects with a large surface area compared to their mass, like a feather, this effect is huge. That's why a feather drifts down slowly, while a stone drops quickly in air. But in a vacuum, with no air resistance, both would fall together at exactly the same rate. This is why we say g is theoretically the same for all objects, but the actual motion we see can vary depending on conditions like air density, shape of the object, and velocity. To recap, acceleration due to gravity is the constant rate of increase in velocity for any freely falling object caused by Earth's gravitational pull. It's derived from Newton's law of gravitation and is determined by the mass and radius of the Earth. Near the Earth's surface, its standard value is 9.8 meters per second squared, but it varies slightly with location, altitude, and planetary body. This concept is not just important for dropping objects, it's at the heart of understanding satellite orbits, planetary motion, space exploration, and even how we walk here on Earth. So, whether you're thinking about Galileo's falling spheres or astronauts on the moon, remember, G is always working silently in the background, shaping motion everywhere in the universe.